Hello, my name is Brian Lee, and this is the video report for Lab 4 in Week 10 of Principles of Physics. In this lab, we'll be discussing a situation in which a mass is attached to a spring swinging in an arc, or in two dimensions in a way that can be described as an oscillation. We will come to see that a computational model can be used to predict the motion of this spring mass system, and that different types of energies and their relationship to one another can be displayed in energy diagrams, all in an environment with no change in total energy. Bearing in mind that all of this takes place on Earth's surface, we can take force of gravity to be the magnitude m times g in the direction negative y hat, which points downwards towards Earth. Spring force is negative k times L minus L naught multiplied by L hat, where L hat points from the base of the spring towards the opposite free end. The expression L minus L naught is known as stretch or compression depending on the sign of the value, positive for the former and negative for the latter, and it also determines whether the force points towards the base or away from it respectively, since the spring wants to return to its relaxed length L naught. Net force will only need to consider those two forces in this case. The velocity and position updates are relevant once again, and so are the energy formulas. Kinetic energy K equals 1/2 m times v squared, and the change in K, delta K, equals 1/2 m multiplied by v final squared minus v initial squared. Gravitational potential energy U sub G equals m times g times y, and delta U sub G equals m times g times delta y. Spring or elastic potential energy U sub S equals 1/2 k times L minus L naught squared, or 1/2 k times S squared, delta U sub S being 1/2 k times S final squared minus S initial squared. Total energy E is the sum of the aforementioned energies, and delta E is just the sum of the changes in these energies. Here's the video reference used for the tracker analysis. It shows a mass attached to a spring that is let go from a non-equilibrium position, such that the mass moves in both the x and y directions. There are two systems in consideration really. One consisting of the mass by itself in order to predict its motion, and another spring mass earth system in order to predict the energy changes in the system. The fixed attachment point, where the base of the spring is, serves as the origin. The surroundings are the spring and the earth for motion prediction, and nothing for energy prediction. As for initial conditions, spring stiffness K is 6.83, relaxed length L naught is 0.123 meters, and time t initial is 0.57 seconds. Here's the underlying code of the computational model. The physical qualities of the objects, for example the mass of the weight and the relaxed length of the spring, were given by a separate video reference that uses the same materials. The energy and change in energy formulas shown previously were used to update and predict each respective value per loop. And here's the output of the computational model, where the red mass represents the experimental data stored via a CSV file, and the blue mass represents predicted motion of a mass given the initial conditions from the video reference. The model simulates the real-life path relatively well, only diverging slightly towards the end. The energy diagram shows the relationship between delta K, delta U sub G, and delta U sub S, and how they sum to a total change in energy of 0, which makes sense since if the system were the spring, the mass, and the earth, then there should be no other force interaction that does work in the system. The resulting position comparison graph shows how the shape of the paths line up, such that the model almost appears to be following the original with only minor differences in the maxima and minima. Some potential sources of error include incorrect initial conditions, other forces at play in the video not considered such as air resistance, and movement along the z-axis that is also not considered. In conclusion, the motion of a spring mass system can be predicted when given its physical properties, such as mass and spring stiffness, and in finding the motion, we also found that the spring mass earth system satisfies the energy principle as all changes delta K, delta U sub G, and delta U sub S sum to 0, suggesting that the net force acting on the system is 0 or that no work is being applied. An oscillation period estimate based on experimental x positions result in an average of 1.652 seconds, while one based on y positions is 1.52 seconds. Given that the motion is an oscillation, the path is more time-consuming or even just generally longer horizontally than it is vertically.